Hi, this is Ryuichi from Rice University. This poster describes our exploration of strategies for efficient modeling of seismic wave propagation on graphics processing units. Much of the prior work on accelerating stencils on GPUs has focused on low-order stencils. Here, we focus on how to accelerate high-order 25-point stencils on GPUs. The data domain for the computation consists of an inner region surrounded by a perfectly matched boundary layer known as the PML region. The computations in the two regions are different. So to avoid branch divergence on a GPU, we decompose the domain into 7 rectangular slabs that each contain points from a single region. The 7 slabs are the inner region, along with PML slabs with 6 subregions. Some of our implementations use 3D blocking, which divides each data region further into axis-aligned 3D blocks. Other implementations use 2.5D blocking, where we partition the data domain along the inner 2 dimension into 2D tiles, and we stream each 2D tile along the outermost dimension. We implement several code versions. Each has its variant of different block dimensions. We have a 3D blocking implementation only uses global memory, and others use shared memory. Additionally, we have a 2.5D blocking implementation that loads all 2D planes needed for computation into shared memory. What's more, we investigated in using registers on the streaming dimension. We tried both shifting the values in registers when streaming and using loop unrolling to avoid unnecessary data movements between registers. We also applied the semi-stencil approach on GPUs, which to our best knowledge is its first application on GPUs. We further optimize our kernels for performance. First, we use pinned memory to avoid extra copies of data and to minimize data movement. We use constant memory, and that reduces register footprint. Furthermore, we design our data layout for better cache line alignment. Besides, we use loop unrolling to avoid unnecessary value shifting among registers. Moreover, we use function template to enable dead code elimination. And also, we use double buffering to hide memory latency, and on A100, we use its newly introduced asynchronized memory copies. We evaluated our implementations on several generations of AMD and NVIDIA GPUs. In this poster, we select a few well-performed kernels on 3 platforms with the latest AMD MI100 GPU and NVIDIA V100 and A100 GPUs. We compare our results with a baseline implementation using OpenACC, and our top performers on V100 achieved about 3 times the speed up. Our A100 provides an average of 6 times speed up, and our best implementation using semi-stencil has almost 7 times speed up. The MI100 results are on par with the performance of V100. The roofline chart shows that our kernel's performance is close to the limit imposed by the GPU device memory bandwidth. It is worth noting that neither the baseline implementation nor our initial attempts were this close to the roofline. We achieved excellent performance as a result of exploring a large collection of optimizations. So this concludes my lightning presentation, and if you are interested in our work in detail, the PDFs of this poster and our paper are available by scanning the QR code on the screen. Thank you for your attention.